All right, open up your book to section 2-7. So on page 110 in your book. Title of this section is Logistic Functions for Restrained Growth. First thing to note there is it's logistic, it's not logarithmic. That's a different function. Logistic functions for restrained growth. So the objective is to fit a logistic function to data with a restrained growth. So what exactly do we use a logistic function for? What's the purpose? Well, the title kind of gives us the purpose here of this, but it's used to model data that has a restrained growth. We're usually talking about a population that's growing over time, or it could be decreasing over time. And it has some restrained growth. In other words, there's some maximum that we can achieve in terms of our population. So the population has a maximum carrying capacity is how we describe that. Most things, when you consider the rate at which they grow and you consider what the maximum population is, it will have a restrained growth to it. You know, if I had a container here that, let's say I had a fish bowl here and I just put one fish in there, one little goldfish, he'd swim around pretty happy. If I added a second one, he might be happy that he's got a little friend in there with him, but he realizes that he's only got half the space then that he can call his own. And as I keep adding goldfish to that, I add 3 or 4 or 10 or 100, at some point in time, that little goldfish can't move anymore. There's not enough oxygen in the water. There's not enough food source for him to get to all the needs that he has. So it has a maximum population for that fish bowl that I have there. There's a maximum population of goldfish that can survive in that space. And if you think about any population growth there, a pretty good chance that it's got a restrained growth there, a maximum carrying capacity for that population. All right, so let's take a little comparison here between the logistic function and the exponential function. And they give this to you there on page 111 in your book. The two functions that we're going to look at here are these two functions. F of x is equal to 2 to the x. That's an exponential function. And g of x is equal to 2 to the x over 2 to the x plus 1. That right there is a logistic function. That's not normally the way we write it, but just for ease of seeing the comparison and how they are related to the exponential, that's why we're going to write it for right now. You'll see, though, that it looks like a rational function because it's got a numerator and denominator to it. And that the numerator is some exponential function, the denominator is some exponential function. In fact, the denominator is just a little bit bigger than the numerator. The numerator is 1 less than the denominator. This is your logistic function that has a restrained growth to it. All right, so let's take a look at what the sketch of these functions would look like, and we're going to plot these here in just a second, but let's grab our calculator and see what they would look like. Let's graph these two. So in y1, let's put in 2 to the x. And in y2, let's put in 2 raised to the x, and we're going to divide that by the quantity 2 to the x plus 1. All right, and let's just look at this on a window. Let's go from probably like negative 5 would be okay to 5. In fact, I'll do that in both the x and the y direction there. That should be a decent sketch of what we want. So there's our exponential function in blue, and there's our logistic function in red. You'll notice that as we sketch this, that the logistic function is following the exponential function over here in the negative domain. So for a chunk of the domain, they stick together. But then all of a sudden they start separating, and the exponential function just continues to grow without bound. That's why it goes off the top of our screen. But the logistic function looks like it's leveling off and approaching some maximum value. It has a carrying capacity. It has a restrained growth, which is exactly what we've got there. So let's sketch those two. So again, our exponential function kind of did something like this, right off our screen. This is f of x equals 2 to the x. Whereas our logistic function, they kind of hung out together there in the negative domain, but then all of a sudden this kind of leveled off. It looks like it was actually leveling off around 1 is what that sketch looked like. This was g of x equals 2 to the x divided by 2 to the x plus 1. Okay? So there's the difference between the two. Again, it's tricky to tell the difference between them if you're only looking at the small values here over on the left. Which is why when you're looking at a set of data, if you're only looking at a small set of data, it can really mislead you. The data could look like it's exponential when it's actually logistic, because those two look very similar over on the left. It's not until you go further and further out, further and further time passes, in other words, that then you can start to see them separate, and you can actually see, okay, is this logistic or is this exponential? All right, a couple things to note there from the graph. If you look at what's happening on that logistic function and consider what's happening as x goes to infinity, as it goes further and further to the right, we'll use this little arrow here to indicate we're headed towards infinity. Infinity is not a number, so we can't be equal to it, but what happens if we go further and further to the right? Well, take a look at that equation and notice what happens here. I'm going to replace the x's in g of x with infinity, so it's going to be g of x is headed towards this value of 2 raised to some really big number. We're calling that infinity there. So we've replaced that x with infinity. And we're dividing that by 2 to some really big number, to the infinite power. We're replacing that x with infinity plus 1. Now if you consider what we have here, in the numerator you've got 2 raised to a huge number, which is in turn a huge number. In the denominator, you've got 2 raised to a big number, but then you're adding on this tiny little value right here. In fact, it is so tiny that adding 1 to the 2 to the infinity, in essence, doesn't even really change the number. The number's so huge compared to adding 1 to it. So that's why in the next quotient that you see there, we've eliminated it. We've eliminated the plus 1 there because of the fact that it's so small, so insignificant. And so what you really have here is the numerator's headed towards 2 to the infinite power. The denominator's headed to basically the 2 to the infinite power plus a tiny, tiny little bit. And since the numerator and denominator then are essentially the same, they differ by just a slight amount. When your numerator and denominator are the same, that means you're equal to 1. So I would expect that when I look at this graph, if I look at what's happening as I head towards infinity, as I head further and further to the right, that I'm approaching a horizontal asymptote at 1, which is exactly the sketch that we see here. As I head further and further to the right, my function is approaching a horizontal asymptote of 1. It's not increasing without bound like we see for that exponential function. Look at what happens in the other direction, which is the same thing that happens with an exponential function. If you let x go to negative infinity, go to the left. As x goes to negative infinity, what does g of x do? Well, the numerator becomes 2 to the negative infinity. Again, I'm going to replace the x there in the equation with negative infinity, same in the denominator. And if you take 2 and raise it to a negative infinity, 2 raised to a really, really big negative number gets really close to 0. It's not quite 0, but it's getting closer and closer and closer to 0. So that's why in the numerator, we've replaced the 2 to the negative infinity with 0 this time. And in the denominator, same thing happens, right? 2 to the negative infinity, that's basically getting really, really, really tiny, really, really fast. And so what you end up with is a 0 in the numerator over 0 plus 1 in the denominator. That, in essence, is headed towards 0. 0 divided by 1 is 0. So I would expect that when I look at the sketch of this graph, and look at what's happening as I go further and further to the left, that it must have a horizontal asymptote of 0. And I didn't mark it in there, but that's in fact what we have here. There's a horizontal asymptote on both of these graphs of y equals 0. All right? And this is the reason why, is because of the analysis that we can make of what's happening as I go further and further in each direction. All right, so what's the general form that we write a logistic function in? Again, I said that the form you saw up above there is not the general form that we usually write it in. although it is a logistic function that way, but here's how we normally write it. If you take that function that we have there, 2 to the x over 2 to the x plus 1, and if we multiply it by a clever form of 1, clever form of 1 means that you have a fraction that you're multiplying by that has the same numerator and denominator. So if I multiply it by 2 to the negative x over 2 to the negative x, that's a clever form of 1. Notice what happens in the numerator. You have 2 to the x times 2 to the negative x. You add the exponents. That's actually 2 to the 0. Anything to the 0 is 1. The same thing happens down in the denominator. You got to distribute to both terms here. Don't forget that this goes to both terms. So I got to distribute this to this term, and I got to distribute it to that term. So when I multiply 2 to the x times 2 to the negative x, again, just add the exponents together there. That's 2 to the 0. That's 1. And then the 1 times 2 to the negative x, of course, is just going to be 2 to the negative x. This is the form you'll normally see a logistic function written in. It's got some constant. We'll talk about what that is here, but there's some constant divided by 1 plus, and then it looks like an exponential function with a negative exponent, is normally the way it's written. All right. So with that, here is the equation that we're going to use here for our logistic function. This comes directly from what we just had on the previous slide, but we're going to generalize it. And actually, we're going to use a base e for our exponential function. That's normally the base you'll see used for a logistic function. So we have y is equal to c divided by 1 plus a times e to the negative bx. Again, it looks like it's some constant divided by 1 plus, and then it's some exponential equation with a negative exponent, which is what we've got there, a times e to the negative bx. Couple of values that we'll throw out there that will specify that need to be true here. A has to be greater than 0. B cannot be 0, otherwise, again, that's a trivial case there. You'd have e to the 0, which is 1 in the denominator, and C is our carrying capacity, so it's going to be a positive value there. Those are generally the restrictions we have there for our logistic function. Depends on the value of B here as to whether or not, as to what this thing looks like. B could be a positive value, or B could be a negative value. Realize the exponent is written as negative B. All right, we're talking about the B value itself then. If B is positive, then the exponent stays negative. If it's negative, then the opposite of a negative becomes a positive value. So it depends on what that value is there as to what this looks like. And it determines whether this is an increasing or decreasing exponential or logistic function here. So if B is greater than 0, we'll end up with a carrying capacity up here that's equal to C. Well, that's what the numerator actually tells us. It tells us the maximum population. You'll have another horizontal asymptote over here on the left of 0. And then the graph will look much like the graph we just had a second ago, where it'll increase, and then it will approach that upper bound there. Okay. And on the other hand, if it turns out that the B value is negative, then you have actually a carrying capacity. We'll put it up here. You have a horizontal asymptote here along the x-axis. And now our sketch here is actually really just a horizontal reflection. Looks something about like this. Okay. Again, all we're talking about is a horizontal reflection because you're taking the opposite value of B, which is the dilation factor in front of x. All right, so that's the possible sketches we could have here for this, depending on the value of B. Here is the parent function. The parent function would be written in terms of a base B, exponential in the denominator. So you have C over 1 plus a times b to the negative x. And some of the problems in the book, you might find them using that one to set up and solve to find the equation of your logistic function. But like I said, for the most part, we're going to stick to the base E exponential. Here's the transform function. If you add in a vertical translation there, you'd end up with C over 1 plus a times e to the negative bx plus d. So if you didn't want to have a horizontal asymptote there at 0 on the left, and you can shift it up there. Just realize now your carrying capacity or your maximum is now C plus D because you shifted that whole thing up. But you could certainly do that. And in terms of domain and range for this function, again, if you take a look at the two sketches there, you should be able to determine these pretty straightforward. But the domain is all real numbers. It goes on from negative infinity to positive infinity. And for the range, you're limited between the two asymptotes that you see there. So you have one asymptote at 0 and the other one is at C on that general equation up above. So it turns out the range is from 0 to C, 0 less than y, which is less than C. All right, let's take a look at an example here that's going to have us go through and find the equation of a logistic function. So if you turn to page 112 in your book, they give us this problem here. It says, use the information in the occupied houses from the beginning of this section. And that's what they described at the very beginning of this, if you have not read that section. But they give you a set of data here where you're building houses in subdivision. And they've listed for you the number of houses that you have built at the end of, well, I guess just a couple of months here. So for part A, it says, given that there are 1,000 lots in the subdivision, use the points for 2 months and 10 months to find the particular equation for the logistic function that satisfies these constraints. Okay, so let me list our data that they gave us here. I'm just going to list the 2 months that they specified. I won't worry about writing all these down. So at x equals 2 months, we had 103 houses, and then at 10 months, they have 167 houses. So those are the numbers they want us to work with here. So given that there are 1,000 lots in the subdivision, use the points for 2 months and 10 months to find the particular equation. All right, so we want to come up with our particular equation. The way we're going to do this is the same way that we've done this for other functions, and that is to start out by writing down our general equation here. So this is f of x is equal to c over 1 plus a times e to the negative bx. That's our general equation. And again, it looks like there's 3 unknowns here, but they actually gave you one of these. When they told you that there's only 1,000 lots in the subdivision, that's your carrying capacity. So for us, we know the c value is 1,000 for this problem. So we'll plug that in. So there's our equation. Now if you look at the example in the book there, they're going to use a base b exponential in the denominator. I'm going to do it with the base e. Again, unless they specifically say, I would suggest you're using base e. Our answer will turn out to be slightly different because we're using a different base, but just realize that you can use any base you want here. All right, so let's plug in those 2 points that they gave us here into this equation. So our x value is 2 and our y value is 103. So we have 103 is equal to, and then it's 1,000 divided by 1 plus a times e to the negative b times x. I'm going to write that as just a negative 2b. The x value I know is second, but I'm going to put the constant in front of that b. And then do the same thing for the second one. So we've got 167 is equal to, it's 1,000 divided by 1 plus a times e to the, again, it's a negative bx, and our x value here is 10. So I'm going to write it as a negative 10b. Again, we're replacing the x value there with 10. All right. In order for us to find out our values for a and b, I've got 2 equations, 2 unknowns. So I've got a little bit of work to do first before I can start trying to figure out what a and b are. What I'm going to try to do is get it in a form where I can use that elimination method in order to solve this. But I got, like I said, a couple of steps to deal with here. So the first thing I'm going to do is get rid of the fraction. You can get rid of the fraction by multiplying both sides by that denominator that you see there. So that's what I'm going to do first. So we end up with, when I multiply this 1 plus a e to the negative 2b over to the other side, we end up with 103 plus, I'm going to go ahead and distribute the 103 through there. I think would be a good first step. 103a times e to the negative 2b, and that's equal to your 1,000. All right, so again, take that denominator, multiply both sides by it, and I'm going to distribute that 103 as I do that. I'll do the same thing here. So I've got a 167 plus 167 a e to the negative 10b is equal to 1,000. my two equations. All right, I still got some more work to do with each of those equations. Let me just draw a little line here so I can keep them separate here, keep the two equations together, I guess. All right, so now let's move the 103 over to the other side. So I want to take this 103 and I'm going to subtract him to move it to the other side. And I'm going to do the same thing with the 167. We'll move him over there. So let's subtract those two values. So I still have over on the left side here, I've got 103 a times e to the negative 2b, oops, 2b, is equal to, so 1,000 minus 103, that sounds like 897 is what we should have there. And then we've got 167 a e to the negative 10b, and that's equal to, if I subtract 167, that's 833 is what I should have there. All right, now this looks a lot like a problem we've solved before. That is, I've got this almost what looks like an exponential form here. And if I want to solve for the a or the b, one method that I can use here is elimination. Elimination would tell us, or using the same technique we've used before, would tell us to take and divide these two. Because when I divide these two, the a's here are going to end up canceling each other out. So let's see what happens when we do that. So what do we get? On the left side, when I divide these, I'm going to just leave this as a fraction like this. I've got 103. I'm going to leave out the a since those are going to cancel out. That'll be e to the negative 2b divided by 167 e to the negative 10b. And that's equal to the 897 over 833. If you want to punch that in your calculator and get a decimal approximation, you can. But keep as much precision as you do your calculations later on. I'm going to leave it in that fractional form for right now. All right, so now what do we have? Draw a line here again so I can keep these separate. All right, let's get rid of the constants in front of the left side there. You got 103 over 167. If I multiply by that reciprocal on both sides, it'll move it from the left side to the right side. So I'll have e to the negative 2b divided by e to the negative 10b is all that's left on the left side. And that will be equal to, I've got an 897 over 833 that's already there, and I'm moving the 103 over 167 to the other side by multiplying by its reciprocal, so it's 167 over 103. Again, if you want to punch that in your calculator and get a decimal approximation, you can certainly do that. It'll save you from writing down a bunch of numbers here, but I'm going to keep it in that form for right now. On the left side, you have a quotient of two exponentials, e to some power divided by e to some power. In fact, they have the same base. We have a property that tells us how to deal with that. You can rewrite that as e raised to just some power, and the power is the difference in the exponent. So you take a negative 2b, negative 2b, and you subtract the negative 10b. I'll put that in parentheses just so I don't lose my sign there. E to the negative 2b minus a negative 10b is equal to this, 897 over 833 times the 167 over 103. All right, now this simplifies over on the left. You have e raised to, what do we got there? Negative 2b, and it'll be plus 10b. So that's a negative, or no, that's a positive 8b, right? E to the positive 8b is equal to this product here, 897 over 833 times 167 over 103. Probably at this point, if you're still writing fractions down, you might realize it's probably going to save you some steps there, so save you some writing here if you got the decimal approximation. But to solve this now, to solve for the exponent, this is where we take the log of both sides. We're going to take the natural log because of the fact that that's a base e exponential function we got there. So I've got the natural log of e to the 8b is equal to the natural log of this 897 over 833 times 167 over 103. And again, the reason why we did that is because these are inverses of each other. These guys cancel each other out. You're left with just 8b is equal to that. Let's just solve for b by dividing by 8 or multiplying by 1/8 here. So b turns out to be equal to 1/8 times the natural log of this 897 over 833 times the 167 over 103. Whew. a lot to write down. There we go. There's our value for B. And you can see that's a lot of work to find out our value for B. And now if you go back to one of the previous equations that we have here, you can solve for A. You got to go back and find an equation that involves A, first of all. And then you can solve for the value of A. I guess I'm going to go back to here. And I guess I will pick, it doesn't really matter which one I pick, but I'll pick this top one here. Let's take that equation right there, and I want to solve that for A with our known value for B that we just came up with down below. So we got 103 times A times e to the negative 2b equals the 897 is our equation that we're going to write down. So now we've got 103 a e to the negative 2b is equal to the 897. Let me double check to make sure I got that written down correctly. Yep, that looks like the right equation. Double check yours is written down correctly as well. And let's solve this for A. If I just divide by all this stuff, I'll end up with what A is equal to in one step, I guess. A is equal to the 897 divided by 103 e to the negative 2b, where b is the number that we just wrote down up above. So let's get some decimal approximations for these two numbers here. So grab your calculator, and let's try that out. All right, so on your calculator, let me just get back to the home screen here. Let's evaluate these two quantities here. So B was, that's a long equation we have to type in here, but it was 1/8 times the natural log of 897 over the 833 times the 167 over 103. That should be our value for B. In fact, I'm just going to say store that right into B and do that all in one statement there, so that way I have that value for later when I want it. And then for the value of A, in fact, I'm going to need it for this calculation, right? 897 divided by, and it was this quantity of 103 and then e raised to the negative 2b. And I'm going to go ahead and store that into A while I'm at it. So there we go. There's our two values. Let me grab a picture of that. And we'll dump that in here for us to have. In fact, I'm going to write down those two numbers here on our slide. So our decimal approximation here for the value of B, that first number was 0.0696. I'm going to write a few more digits here just so I have as much accuracy written down as I can. 69 and then 66, I guess is what I'll write down. Okay. And then for A, we got a value of 10.0106. 0106. I guess I'll write another digit since that's what I did up above. So there's our value of A and B. All right. If you check your work with what you have in the book there, what they have in the book there, you'll notice that your value of A will be the same, because that's representing the same quantity in both. But our value of B was that exponent part, and their value of B is the base part. So just realize there's a conversion you have to do in order to compare those two, but just realize that's slightly different for that reason. All right, if you look at part B now, B says to plot the graph of a logistic function from 0 through 100 months. Okay, so let's go ahead and make a plot of this. Grab your calculator again. And go to your y equals menu. Let me get rid of the two functions we sketched earlier. And we have 1,000. We're dividing that by the quantity 1 plus, and this is the nice thing about storing these into variables here. So now I can say A, and then times e raised to the negative bx. And they want me to evaluate this from 0, not evaluate, but to graph this from 0 to 100, I think is what it said there. Yeah, from 0 to 100 months. So let's go from 0 to 100. Probably a scale of 10 would be good. For our y's, I know that I've got asymptotes at 0 and 1,000, based on what I know about this logistic function. So we'll do that. Scale of probably 100 would be fine. And we'll graph that. So there's our sketch of this thing over the course of 100 months. Right? After 100 months, we're getting really close to our 1,000 homes is what that means. All right, so we'll label that as part B. All right, so now for part C. Part C says make a table showing the logistic function fits all the points closely. Now, you're guaranteed your logistic function is going to fit 2 of the points because of the fact that you actually use those 2 points to make the equation. It's the other 4 or 5 points that they gave us, I guess the other 3 points that they gave us, that it's not going to quite be exactly the same. But let's see what happens here. Grab your calculator again. And let's just make a table of values here. Let's go to your table. And we'll, oops, table set, sorry. And let's start it out at 2. And let's go by 2s is what they want us to do. It's every 2 months. And we'll just have it generate for us a set of data here. So again, at 2 months, you can see you're at 103 like we'd expect. That's one of the points we used. And at 10, it's at 167. That's the values we'd expect there, although there technically is a slight rounding error there in the value you see down below. But the other values are close. If you look at 4 months, it should be 117. We're at 116.6. That's pretty good. At 6 months, it's supposed to be at 132. We're just below that at 131.7. And at 8 months, we're supposed to be at 148. We're just above that at 148.5. So that's pretty good. In fact, I'm just going to grab a picture of that and paste that in. In fact, I'll put it over here. That'll be part C for us. All right, for part D, it says use the logistic function to predict the number of houses that will be occupied at the value of x corresponding to 2 years, and which process do you use, extrapolation or interpolation? Well, we can answer the second part of this, I guess. Extrapolation versus interpolation is determined based on where the data point they're asking you to examine falls within the set of data that they gave you initially. So they gave me sets of data, or a set of data between 2 months and 10 months. They're now asking me to extend this to 2 years. That's outside, so it's not inside. Inside is interpolation, outside is extrapolation. So this is extrapolation is what this is. And I think they just point that out to you because you got to be very careful with the extrapolation. Interpolation is not quite as dangerous. Extrapolation, you really start making some predictions outside of the set of data. And you could be wrong with your approximation there. But anyways, they asked us to do this for 2 years. Now this is in terms of months. There are x values. So 2 years would actually be 24 months. We want to find f of 24 is what we really want to find. And that didn't quite land in my table over there. So let me grab the calculator there. It's the next one in the table of data. In fact, we'll just go to our graph and we'll just trace it to 24 months. And we get 347.105 is our value that we should have there, 347.105. And that would be, what is this, houses, right? Yeah, the number of houses. And finally, the last part of this question, part E, says find the exact value of x at the point of inflection, and what is the real-world meaning of the fact that the graph is concave up 4 times before that and concave down after that. Well, so for part E, if you know you've got a carrying capacity of 1,000, let me go back to this sketch that we've got here. I've got a carrying capacity up here of 1,000, and you've got a horizontal asymptote back over here of 0. The point of inflection actually occurs halfway between those, so the midpoint is what, is 500 then, right? This would be 500. So this is the point they're looking for us to find, is where exactly do we hit a y value of 500. Okay, so that's actually what we want to do here. Let's set our function equal to 500. That's the work we need to write down. We want to find out where f of x is equal to, we actually calculated the midpoint, so it's 1,000 plus 0 divided by 2 is really what we did there. That's how we got 500. So let's just go back to our calculator and have it find that value of x for us. We just found at 2 years, or 24 months, that we had 347 houses, so it's going to be a little bit past that. So let's go to your y equals menu. We'll just dump in y equals 500. And we'll get an intersection there that we can find. If you go to calc, second calc, you can go down to intersect. And just give it your two curves. And I've got an approximation somewhere back here. There's only one solution, so it would find it. So it turns out it's 33.069 months. 33.069 months. So x is equal to 33.069, and that's in months. And then they asked us to explain this. What does it actually mean? Well, prior to that point, your function being concave up means we describe that as increasing at an increasing rate. So that means you're selling houses faster this month than you were the previous month. That's prior to the 33-month mark. And then after that, that means it's increasing still, but it's at a decreasing rate. So that means each month I'm selling fewer houses than I did the previous month. And that's how I start getting closer and closer to that horizontal asymptote, or our carrying capacity. All right, that is the end there of section 2-7.